All right, I think we're ready to start. It's a pleasure to welcome Matei Ciocarlie, an old friend of mine. And Matei did his PhD at Columbia and has spent several years at Velo Gripper. That's where we first met, doing some really seminal work on grasping and grasp planning and manipulation. You see some of the wonderful videos of the PR2 in several labs doing magnificent things, and a large part of it is because of their really wonderful work with the manipulation stack and the grasping stack that they built up. And then subsequently, Matei spent a little bit of time at Google and now is a professor at Columbia. So today he promised me that he'll talk about his entire history of work in the 45 minutes that he has to present it. But welcome to Matei.
Thank you. Thanks for having me, and thanks a lot, Sid. That was a most kind introduction. Hope to live up to it. So good afternoon, everybody. Thanks a lot for coming. Trying to pack a lot of things into 45 minutes. So one thing that I thought I'd do, especially for this audience of roboticists, I'm not going to spend any time arguing for why it's good to have versatile manipulation. I'll assume that's a given. We have non-versatile manipulators. We want versatile manipulators. We want robots that are able to manipulate in people's homes, in the world around us. I'll just take it for granted that's what we want. How do we get there? So a lot of my question is, how do we achieve more versatile manipulation? How do we get from there to there? And when I think about versatility and robot hands, more often than not, I find myself thinking along this two-dimensional space. Right? On one axis, you have how versatile your manipulator is, how capable, and then on the other axis, inevitably, well, how complex it is. And the human hand is all the way in the top right corner. It's incredibly versatile. It's not the most precise manipulator. It's not the most powerful manipulator. It's by far the most versatile, by orders of magnitude. So it's a log scale, if you want. It's also incredibly complex, so complex that we don't even understand a lot about how it functions. So then, okay, the question is maybe how do we get up there, starting from from scratch, from zero. And the first thing that for me that I will argue is the path that we'd like to avoid in our attempt to get to the human hand is this path, where we say, you know what, let's copy the human hand, and that's how we end up with mechanisms that are extremely complex, that go up in complexity very quickly, but the gain in actual capabilities is small. We have these complex mechanisms that we don't really know how to use. And we keep making these hands more complex, hoping that one day we're going to reach this wonderful inflection point where our hands will be anthropomorphic enough that all of a sudden they'll be able to do a lot of what the human hand does. I think that's a dangerous path to follow. Maybe there are better ways. So starting to think about what is one of the things that makes the human hand so difficult to replicate, that is for us as roboticists the most difficult to use for when having either the human hand or a robot hand that's anthropomorphic. So here, for example, is a model of the Robonaut hand, the Robonaut 1 hand, which has 14 degrees of freedom. The human hand is often modeled as having 20 degrees of freedom. So this is slightly older work where we started from this problem that if you have this very, very high dimensional posture space where every joint is one axis in your high dimensional posture space, and then any hand posture, any grasp is one point in this very high dimensional posture space. This is my best attempt to take a 14-dimensional space and illustrate it on a 2-dimensional slide. So grasp planning, right? We have an object, we want to find a hand posture that is a good grasp of that object, means finding just the right little points in this 14-dimensional space for this hand, 20-dimensional space for the human hand, finding just the right points in this very high dimensional space that form stable grasp. And computationally, that's a very, very difficult problem. It's, to some level, an intractable problem. How do people do it, right? We are very good at it. You give me a new object, I immediately come up with a hand posture for grasping it. And for a long time, there's been this intuition that somehow people simplify this problem. How do we simplify it? Well, maybe one way in which we simplify it is that we don't really bother to search all that very high dimensional space. Maybe there are some pockets, some clusters, some discrete clusters in that very high dimensional space, and most of the grasps we use fall somewhat in there. And this is the notion of a grasp taxonomy that says, maybe this cluster represents power spherical grasps, this cluster has cylindrical grasps, maybe here we have pinch grasps, and we really care about searching these little discrete pockets. And many taxonomies have been proposed over the years. I think Napier was one of the first. Mark Katkowski's work was one of the most influential that's been used, that's still very actively being used today. So that's one hypothesis about how to simplify the search of this very high dimensional space. A little bit more recently, Marco Santillo and his colleagues, they are kinesiologists, they said, what if instead of looking for those discrete pockets, there's a continuous subspace in this high dimensional space that has most of the grasps we need? And here, unfortunately, it's very hard to see. There's a plane that is illustrated here, but the colors wash out in the projector. So what if most of the grasps that we care about really fall on a low dimensional manifold in this high dimensional space? So they collected data of hand postures for people miming grasps of household objects, and they ran principal component analysis on that, and they found, I think even they were surprised to find that just two principal components accounted for 85% of variance in the data. So really just a two-dimensional hyperplane accounted for 85% of the variance in the hand posture in that very high dimensional space. The two principal components that they found, these are the two. This is one of them. So this is movement along one of the two basis vectors that define that hyperplane, and this is movement along the other basis vector. And sort of looking at them qualitatively, to me, they also have intuitive meaning. One of those principal directions, you can think of it as scaling the hand from grasping a large sphere, grasping a small sphere. The other one has opposing motion in the MCP versus the IP joints. So when this one extends, these flex, and the other way around. So you go from this to this. So maybe from grasping a pinch to grasping something against your palm. So you combine those two, you get a lot of the variance in hand posture that we need. So then what we said was, if we think of these as, we refer to these directions as eigengrasps. So the eigengrasps are the basis vectors that define this faint hyperplane that probably none of you can see on the slide. So what if we search for good grasps only inside of that hyperplane? So if we have a search algorithm that only moves in the two-dimensional subspace, that really simplifies the search, because now you're no longer dealing with 20 dimensions, you're only dealing with 2. Maybe that can get you so close to a good grasp of an object that then, when you finally have to leave the hyperplane and actually grasp the object, you can do that just completely open loop. So this is what our search looks like. I think I need to click this guy. So this is a simulated annealing search where it's trying to match the shape of the hand to the shape of the object, and the hand posture is only being explored in that hyperplane that I was showing you. So only in that two-dimensional subspace. Simulated annealing is pretty good at these kinds of searches where your quality function is very discontinuous. You let it run for maybe in this case up to a minute. These are the kinds of results that we were getting. So these are all hand postures optimized in that low dimensional subspace. And from most of these, if you now just do an open loop, close all the fingers, so you let just contact with the object give you that little bit of final refinement that you need to get a perfect grasp, you do tend to end up with a stable grasp in most of these cases. So ultimately, this result showed, look, even for something as complex as the human hand, and again, here we have the human hand on the bottom, a whole bunch of different robot hands on the top. Once you've defined this low dimensional subspace for a robot hand, the algorithm runs identically on all of them. So there's nothing different between the human hand, the Robonaut, the DLR1, or even the batted hand. So the algorithm runs the same way. And you can really simplify this problem of grasp planning, of finding appropriate hand postures, from many, many dimensions to a subspace that has a lot fewer dimensions, that's a lot more efficient to plan in. So in a sense, going back to thinking about hands in general and complexity versus capabilities, we were thinking of eigengrasps as a way of saying, look, we can reduce some of the complexity associated with the human hand and hopefully not throw out the baby with the bathwater, not lose a lot of versatility in the process. So we are only planning in 2 dimensions of hand postures, not 20, big reduction in complexity, but because it's the right 2 dimensions, the loss in capabilities, the loss in versatility is not that big. For grasping, of course, if you want to play the flute or play the piano, those 2 eigengrasps aren't going to do it. But for grasping a wide range of objects, hopefully you can still get a lot of capabilities even while you've reduced complexity and you've made planning a lot more tractable. And in particular, let me quickly switch. Another thing that we did, this is a video that I wasn't going to show, but then Sid very specifically requested it. If the person gives you a hint in terms of what direction to approach the object from, so the planner doesn't have to worry about the 6 degrees of freedom of hand position relative to the object, then we can plan really, really fast. So here we have a human that's telling us how the object should be approached, so then the planner only has to worry about setting the correct finger posture. And because the planner only operates in the 2-dimensional subspace, we can do it fast enough that it's interactive. So here's what's happening behind the scenes. That's the human telling us how the object should be approached. This is the simulated annealing planner that's running in real time, and in a matter of seconds, usually a few seconds, it's able to find a good posture. It shapes the fingers of the hand according to the posture that it found, so then the person can say, I like that, click, close the fingers, go ahead and execute the grasp. And in real life, we show that with the battered hand. In simulation, we show that we can find appropriate grasps really, really fast at interactive rates, even for something as complex as the human hand. So switching back to the presentation. So again, this was the work that was starting from the human hand and saying, how can we simplify the problem for something as complex as the human hand? But there's another way of looking at the same goal. How do we get up there? One way is to start from the human hand and try to simplify it. Another way is to say, if we start from nothing, blank slate, and we want to build robot hands, that eventually we want them to be very capable, and complexity, we want to keep that in check. How do we start? Where do we go? Where do we go from here? And arguably, what's the very first thing that you need if you're going to do robotic grasping? And arguably, it's 2 forces that oppose each other. If you're going to grasp, you need 2 forces in opposition. So then, according to that line of reasoning, the very first thing that you build, if you start from scratch, is a parallel jaw gripper, like the PR2 gripper. And indeed, the parallel jaw grippers are widely used, very successful in industry, and on the PR2 we use them on many other tasks. Okay, so this gives you the most bang for the buck if you start from nothing. What's next? Let's say you're trying to build on top of a parallel gripper. What gives you the next most bang for the buck? What increases capability the most but doesn't increase complexity? And if you play with parallel jaw grippers for a long time, one of the things that immediately starts getting to you is just how bad they are at specific types of grasps and specific types of disturbances, right? If I'm holding something in a parallel grasp, resisting this disturbance is one of the hardest things for me. Resisting a torque around the axis of contact. I have to squeeze really, really hard if I want to resist this particular disturbance. Because a parallel gripper is just intrinsically not well suited for that. So again, arguably, the next thing that you want in your gripper is not to just be able to do this kind of fingertip grasps, but you want it to also be able to envelop objects. Once you can do both parallel and enveloping grasps, that increases the range of objects you can hold stably a lot. And this is what my practical experience has taught me. So how do we obtain that kind of performance? How do we get these behaviors while keeping complexity as low as possible? And one way to do that that's been very, very successful for us, I think, as a field in the last 10 years or so, has been this, more than 10 years, because the battered hand, obviously the design is a lot older than that, is the idea of let's try to achieve high capabilities with low complexity by leveraging passive mechanical adaptation. You can have a hand that's very capable but not complex if instead of having lots of motor and a lot of active control, you have hands that just passively comply to the shape of the object that you're grasping. And there are some very successful examples of that. The battered hand was built according to those principles. Robot IQ, the Harvard hand, and then later the DARPA RMH hand. All of these meant to inhabit this region of this space of excellent capabilities with low complexity by leveraging passive mechanical adaptation. So for us, again, going back to the goal of doing fingertip grasping and doing enveloping grasping with as little complexity as possible, that meant, can we do it with a single actuator? Can we build a hand, a gripper, that to achieve those kinds of grasps, you need at least 2 fingers, at least 2 links per finger? Can we do it with a single actuator? Can we build a gripper such that if it's closing unobstructed, you get the behavior in the top row, where the distal links stay perfectly parallel to each other, and then what you get is the behavior of a parallel jaw gripper, which is very effective because it gives you nice parallel grasps of a range of objects. But on the other hand, if you do encounter something, then you get this behavior where the distal links continue to flex in, and you passively get an enveloping grasp of your object. So that was the behavior we were after in building the gripper to come after the parallel jaw gripper on the PR2. So how do we achieve this behavior? So first, just mechanically trying to get this behavior where we have perfect parallel distal links as long as you're not hitting anything, but then the distal links can flex in if you are hitting something. One way to achieve that is with a unilateral constraint implemented in hardware. So if you imagine a 4-bar linkage here, so we have 2 joints here and then essentially a 4-bar linkage, this mechanism ensures that the distal links stay parallel as the finger closes, but then if one of the bars is soft, it's a piece of wire, it allows the link to flex in, right? So here you can imagine that this link can never flex, can never extend, can never hyperextend, but this piece of wire can simply lose tension and then the link can flex in. So it's a unilateral constraint that prevents hyperextension, allows for flexion. So this is the conceptual implementation. In real life, we just have a tendon that goes over equal radii pulleys on both of those joints. So that takes care of the parallel constraint. The next question, though, was what dimensions should we make the thing? Because if you're trying to envelop objects, dimensions matter, right? So that's just right. The gripper relative to the object is the right size. That's too big. The object is too big relative to the gripper. We cannot envelop it. The object is too small. And because we have only 2 fingers that are not offset out of plane, the fingers hit each other and you don't get an enveloping grasp. So what is the ideal size, the ideal lengths for all the links that give us good performance over a wide range of objects? So then what we did is we thought, okay, let's look at 2 kinds of objects, ellipses and rectangles. And we took and we measured a whole bunch, I think close to 100 common objects, common household objects. Bottles and mugs and cups and staplers and computer mice. And in this space of objects, width versus height for elliptical objects, and then width versus height for rectangular objects, we just plotted where all these objects are. And then we simply ran an exhaustive search asking what are the link lengths that give us good enveloping grasps for as many of these as possible. And what we ended up with is this. So the blue dots show the areas where our gripper can do effective enveloping grasps. It's Honestly, it wasn't as big as we hoped it would be, the blue area. It was an exhaustive search, so we knew that really we cannot really do any better. But still, we can envelop all of these objects, and we very explicitly said, you know what, if we can have this part where we're good at enveloping, it can either be good at enveloping large things, it can be good at enveloping small things. Small things tend to be lighter, so maybe for small things we are okay with doing fingertip grasps. So maybe it's better for us to just focus on enveloping the large stuff. So this is what gave us the lengths of the links, the kinematic configuration. And then finally there's the question of, okay, the kinematics are not enough. We have to care about forces. Once we've actually enveloped an object, keep in mind that we have a single actuator. There's a single motor that's pulling on the tendon that's flexing both fingers, right? Is this a stable grasp? Because if you only have a single actuator, if you cannot independently change the torque that you're applying at the proximal joint versus the torque that you're applying at the distal joint, if these torques are not in the right ratio, the grasp might not be stable. You might eject the object out, or the fingers might slip on the object, and you still lose the object. So how do we get stability for grasping in as many cases as possible? So this is the design for our gripper, and we have a number of parameters that we can play with. This is the one flexor tendon that flexes both joints for both fingers. The flexor tendon is routed over a number of routing points. We have an extensor tendon that's connected to a spring, which is entirely passive, which gives us the extension forces. We can also have torsional springs in the joints. And then all of these things we can tune. We can change the location of the routing points. We can change the stiffness of the springs. So then what we can do is we can try to characterize the behavior of the gripper as is grasping an object. If we apply a certain force to our one and only active tendon, we can compute what are the resulting torques around each of the joints. Because we can simply add up the contribution of the flexor tendon, the extensor tendon, the springs, and gravity. So we know if we pull here, those are the torques that we're getting around the joints. If we have contacts with an object, in order for the grasp to be stable, we also know what torques we would need around the joints. Are those torques the same? Is the torque that we're getting from actuation the same as the torque that we need for stable grasps? And if it's not, we can change our design parameters to make it be the same. So basically, the algorithm that we used to optimize the design was starting from just a random seed. We can compute an error metric based on, are all these grasps stable? Are we getting the right torque ratios between the distal joint and the proximal joint? And then we can compute a numerical gradient, which tells us, hey, this routing point should move a little this way. This routing point should move a little that way. This pulley should decrease in radius. So we take a step in the direction of the numerical gradient, and we keep doing this enough times until eventually the whole process converges. So then, when it's all said and done, we had dimensions for the links, we had the tendon routes and all the spring stiffnesses optimized using the method that I just showed, and this is the final result. This is the gripper that we ended up with, and you can see here the execution of perfectly parallel fingertip grasps, enveloping grasps, passive extension, and this is showing the range of household objects that it can envelop based on our kinematic optimization for the link dimensions. This is why enveloping is important. This is exactly the kind of task where you really care about being able to resist those kind of torques around your contact axis. We're excited about the ability to passively match irregular object shapes without reasoning about it at a computational level. And this is the same gripper integrated with our manipulation pipeline on the PR2 robot and doing autonomous grasping of a whole bunch of household objects. So this was a lot of this we tested on these kinds of household objects that you'd expect to use that we had lying around Willow Garage. But then an interesting thing happened. We looked at a study of what objects do people want a robot to retrieve for them, right? So no longer just, us saying, hey, the coffee-mate bottle. Let's look at, there's an excellent study from Charlie Kemp's lab at Georgia Tech. They talked to people with motor impairments and they asked them, what objects would you like a robot to retrieve for them? That was an eye-opener for us, because many of those objects were different than what we had looked at until then. They were small things that tend to sit on a tabletop, a pill, a pen, a key, right? So that kind of scenario up there. And that's actually a tough scenario for a rigid robot with a rigid gripper, because you have to be very precise. If you're positioned too high, then you're going to miss the object. If you're positioned too low, you're going to hit the table, and if the arm is rigid and the gripper is rigid, bad things are going to happen. So what happens if we try to grasp these kinds of object with our gripper, the one that I just showed you? So you come in low, and then you hit the table with the distal links. But then, because of passive compliance, as you're continuing to pull on the tendon, the distal links flex in, and then the whole gripper continues to flex until the distal links hit your object. And this is where the interesting part is. What happens now? Well, what can happen is that you have some contact forces that you're applying at each of these contacts, and we can compute those contact forces because we know everything in this equation. We know the force we're applying, we know the spring forces. So if the resultant from these two contact forces is pushing down, then we're good, because the table will support us pushing the object down into the table. So the whole system is stable, is in stable equilibrium. So if this is the case, if we are indeed stable and we're pushing the object into the table, what we can do is we can start moving the gripper up. Eventually the distal links become parallel. The soft unilateral constraint engages, and then you get perfectly forces in opposition, and then you can lift the object off the table. So we did a characterization of our design, asking ourselves for various object widths. So W is the width of the object, and then H is the height of the gripper above the tabletop. And then here, right, so this is object width, that is gripper height above the tabletop. Black means in this region we expect the grasp to succeed, and gray means in this region we expect the grasp to fail. So the way you read this plot, you say, I have an object that's 60 millimeters across that I want to grasp off of a tabletop. I can put my gripper anywhere between 75 millimeters above the table and 110 millimeters above the table, and the grasp will still succeed. Right? This entire line in the black area is between maybe 35 millimeters tall. So that means I have a lot of error that I can afford in terms of where I'm putting the gripper above the table. It doesn't matter how precise I position it, as long as I'm inside that region, this open loop grasp primitive will still succeed. So this allows us to characterize exactly how much forgiveness we have to positioning errors. This is what it looks like in practice, where you can grasp a wide range of objects and the grasping primitive still works. And here you see the robustness to positioning errors relative to the table. So the same object, this is an example of starting off fairly high up above the tabletop, and it works. Now we're a little bit lower, the same primitive still works. Now we are all the way low, and the same primitive still works. So here we are using contact with the environment to our benefit. We're not avoiding contact with the tabletop. We are embracing it and using it, and we can still characterize our grasping primitive and say, hey, this will still work. So going back to my high-level view of hands and grasping, we can take another step. This is the Velo Gripper and other passively compliant grippers. And you can kind of tell that by now, I feel that ideally these two directions should meet at some point. When they do, good things will happen in terms of our ability to address a wide range of tasks for robotic manipulation. Which one is the ideal robot hand? I don't think there is one ideal robot hand. But if we have a curve like this that we can plot, then depending on the application, we know where we want to position ourselves on the curve. If the application calls for not a lot of variability, then we can say, you know what, we're fine in this side of the curve. If we need more variability, then okay, we need to be further higher up. But as long as we keep pushing this curve towards the top left corner, we should be in good shape. What about the software, right? That's another part that I haven't talked about so far at all. This is, you know, we've looked at the hand design. What about the planning software? That's another big part of manipulation that hopefully could help us get more out of our mechanical designs. So one thing that we did at Velo Garage, sort of pretty soon after we had the PR2, we wanted to establish a baseline of performance in terms of what the PR2 could do for grasping. So the first thing you look at in such a case, try to simplify the perception problem, which is a big part of manipulation, and say, okay, if we're doing tabletop grasping, where you know that you're grasping things off of a planar surface, and you know that the things you're grasping are separated from each other. Because then you can segment out the plane of the table, you can cluster each object individually, then you can try to match object shapes from a database to what you're seeing, to the point cloud that you're seeing. Some objects you might be able to recognize, the little bottle, the glass here. Some objects, this is a stapler, you won't be able to recognize, and you'll just say, you know what, this is a blob. For things that we were not able to recognize, for things that were just blobs, my colleague Kai-Jen Shao led the work on writing a grasp planner that used a number of heuristics, like aligning the gripper with the principal axis of the object, but then, very importantly, also used the tactile sensors on the PR2, integrated with those heuristics to do fine position corrections in case unexpected contact happened. For cases where we were able to recognize the object, we used our simulator, Graspit, to pre-compute good grasp locations for the PR2 gripper. And we could run this for, you know, a couple of hours in simulation, and each green arrow shows one good approach direction for a parallel gripper to grasp that object. So then you put all of those together and you get things like this, tabletop grasping demo on the PR2. If with all these assumptions and tabletop grasping, you know, you can make your robot look pretty dexterous and pretty smart. And we were running this demo at ICRA in 2010 in Anchorage for hours and hours and hours in the booth. But again, there were these assumptions that we are doing tabletop grasping. And then a lot of excellent work also on tabletop grasping happened in the DARPA ARM-S program, and Sid was one of the people leading the charge there, and getting excellent results on grasping a set of objects sitting on the tabletop. There were still significant challenges because this particular platform had sensors and actuators that gave you a lot of uncertainty, both in sensing and in execution. So there was still a lot of work to do, but they were able to achieve excellent results. So ultimately, that led to IROS 2012, where Gil Pratt from DARPA uttered his, by now famous, you know, in his famous keynote address, said, "Grasping is solved." And that's us at the banquet, presumably celebrating the fact that as a field, we had just solved grasping. So yes, for tabletop grasping, we are able to do really, really well, but there are still big challenges ahead. Just very quickly at a high level, what are some of those challenges that we looked at? One of them is this problem of uncertainty, right? You have, ultimately, even if you are doing segmentation on the tabletop, that's an object that you've segmented in a Kinect point cloud. That's all that the robot is seeing. What is that? A tennis ball can explain that point cloud. A glass can explain that point cloud. Many other things in between can explain that point cloud. If you treat your perception as a black box and you just take the first result and run with it, you're going to be very sensitive to errors and to uncertainty in your perception. So one thing that we did is we said, okay, what if we actually embrace the uncertainty from our perception algorithm? We ask the perception algorithm not just what's the most likely candidate, give us all the top most likely candidates along with your uncertainty level for each of them, And then we'll try to find grasps that work equally well on all of those possibilities. So that gave us a pretty significant bump in performance. And this notion of, let's embrace the uncertainty and reason about it explicitly. And the other really big direction for me, and this is a collaboration between Velo Garage and Sid's group, and excellent work by Mehmet Dogar, who was here with you guys, looking at what about situations where your environment is constrained, where you cannot afford this notion that, my robot is going to avoid all contact with the environment like it's the plague. The robot's going to look really, really hard at the scene, and then he's going to plan this path, taking great care not to touch anything except for the target object. And then when it touches the target object, it's supposed to instantly transition into a grasp. And that's it. That's the only environment interaction I can afford. That doesn't hold in real life. The robot will have to engage in more complex interaction with the world. But then the problem, if you are interacting with the world physically, is you have to predict what's going to happen, right? And this is, to me, one of the fundamental problems in manipulation. More often than not, for rich interaction with the environment, we are unable to predict the consequences of it. And because we cannot predict the consequences, we cannot integrate it in our planners. So here we said, in this more cluttered scenes, let's try to predict what happens if we try to push obstacles out of the way and get the object into our grasp. So obviously we needed a perception algorithm that would operate in clutter, and this is where our colleagues at Velo Garage pitched in with their textured object detector. And then you can do more interesting manipulation like this. And now, we're starting to look a little bit more human-like with our environment. It's no longer, the tabletop, just that very artificial notion of a tabletop with separate objects sitting isolated from each other. So to me, the two big things for moving past this tabletop grasping thing is, one of them is uncertainty, embracing uncertainty, and the other one is richer and more dexterous physical interaction with the environment. Not just don't touch anything and grasp, have other ways of interacting with the environment. And then finally, the last part of my talk is about the people that are supposedly next to the robot, because arguably the robots don't exist to just move objects from one side of the table to the other. There's somebody who's benefiting from what the robot is doing. And in particular, one project that we had for which this notion of the person was absolutely central was the Robots for Humanity project. This is our collaborator and friend, Henry Evans, who's quadriplegic and mute as a result of a brainstem stroke that occurred about 10 years ago. Henry can still move his head. This is his wife and primary caregiver, Jane. This is how Henry talks. He looks at a board with letters, and then Jane interprets what he's saying. And then, very importantly for us, this is Henry using a computer. So he can move his head. So there's an off-the-shelf commercial product that tracks a reflective dot on his glasses, and converts that into mouse cursor movements. So the computer thinks it's a mouse. As far as the Ubuntu is concerned, it's just a mouse. It plugs into USB. So he can move the mouse cursor, and he has enough residual movement in his left thumb that he can click a button. So essentially, he has a slow, imprecise, one-button mouse. So then for us, the challenge was, how do you build an interface around a slow, imprecise, one-button mouse running on a laptop with limited screen size that allows somebody like Henry to teleoperate a beast like the PR2 with 14 degrees of freedom in the arms, 3 more in the base, the head, the torso, and God knows how many degrees of freedom in the sensor data that's coming in. So how do we bridge this gap between the operator and the robot to allow Henry to do meaningful tasks? And probably at this point, really the only way to do it is to think about shared autonomy, because autonomously the robot isn't going to do meaningful manipulation tasks in Henry's home right now. Teleoperation for Henry is too cognitively demanding. We cannot ask him with his slow one-button mouse to teleoperate the PR2 at a low level. Thankfully, though, autonomy and teleoperation are not these two mutually exclusive ways to do it. There's an entire spectrum, continuous spectrum between them, and you can imagine this slider sort of continuously moving left and right based on how the application dictates. So for the first very concrete task where we thought, let's implement this paradigm, this shared autonomy paradigm, again, we looked at grasping, but we thought, let's look at really, really difficult environments, things where autonomy just fails. So really bad clutter with objects on top of other objects, really bad clutter with really tough obstacles, vases that we were telling people they're full of water and very fragile, and clutter and constraints together. So these are all three environments that for full autonomy are really, really difficult. What about if you put a human in the loop? What are the different strategies along that continuum from teleoperation to full autonomy that you can try? So starting all the way from low-level teleoperation, this is one strategy that you can use. This is the interface that the teleoperator that Henry would see with an image on the left and the Kinect point cloud on the right. And here, the teleoperator is just doing live Cartesian space gripper teleoperation. The teleoperator is in charge of everything, of avoiding joint limits, of avoiding collisions. So the operator has to go ahead and execute the grasp from the beginning till the end, positioning the gripper correctly. And they can use both the 3D view, which they can orient however they want, and the camera view, which obviously is fixed because it's only from the robot's cameras. So this is the most teleoperator intensive strategy that we tried. One that had some autonomy built in, this is where the user doesn't do live teleoperation of the end-effector, but they position a virtual end-effector model in the scene. And that end-effector turns green if the robot is doing motion planning and trajectory generation to get the gripper to where the user is asking it to go. It turns green if the robot is saying, yeah, there is a collision-free motion plan that I can execute to get the gripper there. So then the person just says accept, and the robot goes ahead and executes the grasp. So here the person is just giving us the cognitively valuable bit of this is where the gripper needs to go. And then finally, we also threw what was at the time the best grasp planner that we had for very cluttered scenes. That grasp planner was a little bit hit or miss in clutter. It would come up with decent suggestions for grasps, but still we thought, the person should choose one of these suggestions, and then the person needs to adjust it as needed. And again, the same idea that the motion planning and the collision avoidance would be taken care of by the robot autonomously. So the person only needs to deal with where the gripper needs to go. So then we did a big study with almost 50 novices that had never teleoperated a robot before. And we looked at, for each of these strategies, so least autonomy, most autonomy, and then number of objects grasped and collisions encountered in the process. So we saw a couple of things. First, with more autonomy, kind of a very qualitative impression, more autonomy works. Novice users were actually able to complete the task efficiently, and autonomy helped, which we were very happy about, obviously. Fewer collisions, more objects grasped. But autonomy doesn't always help. So when we were here, we're just doing motion planning for the user. The user is positioning the gripper. We're just doing motion planning. Here, we're also trying to do grasp planning. And there was absolutely no meaningful improvement when also doing grasp planning versus only doing motion planning. So we dug a little deeper, and we understood why motion planning helped, because the kinematics of the robot were very unfamiliar to people. The PR2 looks human-like. It's human-like enough that it feels like, oh, I'm going to teleoperate it like it was my arm. The joint limits are non-anthropomorphic. So a novice user will run into a joint limit when doing live teleoperation that they'll be unable to get out of because they don't understand it. So motion planning helped. But this notion that we're going to give you a grasp planner that is useful, but you have to look at the results and still adjust them, that turned out to just be too much. People either trusted the planner too much or they didn't trust it at all. So very important to be very clear about what autonomy can do or what autonomy cannot do. We had a very similar approach to navigation, where the person would, the high level, the more autonomous approach is where the person just gives you a goal and then the robot drives autonomously to get there. The low level teleop is where the person takes over and does live teleoperation of the base. And overall, we took all of these different ways of doing things and put them into one big framework, which we refer to as tiered human in the loop, where we said, you know what, the robot should be autonomous as much as possible. When autonomy fails, we should ask for the user's help, but at a high level. If we're doing grasping, that means maybe we should only ask the user which object should be grasped. If that fails, then we need to go at a lower level. Maybe here we're asking the user where to position the gripper. If that fails, then we go at an even lower level, and now the robot is saying, I give up, here human, take over and teleoperate me. And hopefully, if we are successful, then we stay in this loop most of the time. We rarely fall back to here, even more rarely fall back to here, almost never fall back to here. And then we can be efficient. This is what this looks like in practice. This is the PR2 in Henry's home. This is Henry's kitchen. And Henry wanted to get a towel from the kitchen, drive back, and wipe his face. This is the very first time we tried that task. Before we tried it, we didn't even know where the towels were in Henry's kitchen. He didn't even actually know either. He opened the cabinet first with the robot, looked inside, there was nothing there, closed the cabinet, opened the drawer, got the towel out, drove back. So the task succeeded in a real home the very first time Henry tried it, which for us was, we were very excited about. The flip side was that it took 45 minutes for Henry to do it, because very often he did have to fall back onto more teleoperator intensive ways of doing it. So still a lot of work to be done, but there's just, it opened a whole new world for us when we had a robot in somebody's real home. You start realizing just how different a real home is compared to the tabletop grasping scenarios that we had been doing up to that point. This is another example. This is at Halloween. One thing Henry said that he wants to do is give candy to children at Halloween. So this is at the local mall in Palo Alto. These are children who are trick-or-treating. They have no idea what's going on. And this is Henry and the laptop that's running our interface, and he's picking up candy from the table and putting it in children's bags. And he happily did it for about an hour and a half. Children were coming. I think children just thought they're getting candy from a robot. They didn't realize that there is a person behind the scenes. But again, this speaks to the power of building general tools, because we didn't wake up one morning to say, the next thing for robots to do is to give candy to children. But if you talk to your user population, they surprise you and they tell you what they need. And then the last bit for my talk, one thing we learned in this, after we had done all that, now we said, how do we improve it? And we realized that low-level teleoperation still happens quite often. The person needs to fall back on that. And it's not very efficient, because novice users just don't really understand the kinematics of the robot, and it's also very hard to keep track of where all the obstacles are if you're seeing the scene through this tiny laptop screen. Situational awareness for the operator is really hard. If you're in somebody's kitchen, in the lab, you're opening the drawer, you're fine. In Henry's kitchen, you're opening the fridge and you're putting your elbow through the oven, which is right behind you, because it's a tight space. It's impossible for an operator to have that kind of situational awareness where all the obstacles are. So then one more piece of work that we did was to improve the low-level teleoperation and say, can we take care of some of these constraints autonomously? So ultimately, the goal is, when you're doing Cartesian teleoperation, the person is telling you how they want the gripper to move in Cartesian space. We want to compute a joint change that achieves that for us. So it turns out that you can put that entire formulation in a quadratic program where you're trying to move towards the goal, so minimize the distance between what results from your joint change and what the person has asked. You want to stay close to a sweet spot where you are away from all the joint limits. So this tells you that you want to really stay as close as possible to this sweet spot over here so that you avoid joint limits. And also, joint limits, not only you want to stay far away from them. If you get too close to a joint limit, it becomes a hard constraint. And also, if you've sensed the environment, either with the chest laser on the PR2 or with the Kinect, and there are spots where you're too close to an obstacle, you're only allowed to move in the direction of the normal. So you put all of these together, and it's a quadratic program. But then the big enabler for us was that in recent work from Stephen Boyd's group at Stanford, they showed that for specific forms of quadratic programs, they can generate C++ code for that specific program, so they can do embedded convex optimization. And each QP of this size, they can solve in a few hundred microseconds. So not milliseconds, microseconds. Which for us was great, because it meant that we can plan a little further out in the future. We can do multiple loops of this iteration very, very quickly. So essentially a way of model predictive control. So when it's all put together, this is what the result looks like. The person is giving you an end-effector goal, and then the robot just avoids obstacles and nicely slides along. You can also take step inputs in case it's a different kind of teleoperation. So this is a step input that the robot is also executing and avoiding obstacles. And it's nice because it also works with continuously changing 6DoF input. So here with the Razor Hydra, the teleoperator is giving you continuously updating 6DoF goals, and then the gripper tracks that and stays away from joint limit constraints and also stays away from collision constraints. Compared to other methods of doing teleoperation, and again, there are some things here too faint to see, right? If you have a starting point in red and the goal in green, if you're doing just straight Jacobian transpose, Jacobian inverse, that just says go in a straight line towards the goal. If there is autonomy in the loop, autonomy can only decide how far along the line to go. And the same with interpolated inverse kinematics. If you're doing global motion planning, if you have, this is the start, this is the goal, and I'm going to plan the path using RRTs or PRMs. Stochastic motion planning is now almost fast enough that you can do this interactively. So in about 500 milliseconds, you can plan a trajectory so that the robot starts moving. So now you can go anywhere and approach the goal from any direction. And then our method, the QP-based method, allows the robot to go in a cone that reduces the error from the start to the goal. So for these two, autonomy has more leeway. Autonomy can decide which way to go, and for us, autonomy can decide which way inside this cone to go to avoid other constraints. This is a comparison of all those methods. So Jacobian transpose, interpolated inverse kinematics, global motion planning, and our method. The top two just immediately get stuck on the obstacle. Global motion planning does these elaborate paths, and it's also a lot less responsive. It takes a while for it to start moving. Whereas the QP method is very responsive because the robot starts moving within microseconds of the person updating the goal, and it also gracefully avoids the obstacles. So obviously there are cases where only global motion planning works. Something like this can get stuck in a local minimum, but for other cases we really like the responsiveness of the QP approach. With the best method for live teleoperation probably combines features of all of these, and we'll have to see exactly what that looks like. So this is kind of some more numerical results, but since they're all in the papers and almost out of time, I'm not going to spend too much on this, so I will just jump straight to the recap and conclusions of all that I've told you about today. So my personal, what I think I've learned, at least after working on all of these projects, that it's really important for robot hands to think about not just the versatility of the hand, but the price that you're paying for that versatility. So to never add complexity to the mechanism unless you can quantify the benefit that it's giving you. And that complexity for the sake of complexity is the enemy. And really try to have provable gains for anything else that you're added. Or try to simplify a complex hand like the human hand without losing versatility. In terms of the manipulation pipeline, the software for the manipulation pipeline, which considers perception, planning, and execution. The two big lessons for me, one was to explicitly reason about uncertainty. If you just pretend the uncertainty doesn't exist and you hope for the best, there's only so much you can do. And that we really need to make more contact with the world in more interesting ways. We cannot afford to keep avoiding contact with the world forever. And then for human-in-the-loop manipulation, in addition to how to give the operator situational awareness, there's also the question of, we need to find the cognitively important bits that are really difficult for the robot to derive by itself, but that for a human, they're really easy, and they're a few bits that the person can provide easily over a high latency, low bandwidth link. And then we can get to more complex manipulation primitives, and hopefully get robots in more interesting environments and outside of the lab. Thanks a lot.
Thank you so much, Matei. We have time for a few questions. I'll let him provide.
You talked about the cognitive important bits. I'm curious to know how much would semantic information about the object being manipulated matter to you, and how do you foresee that impacting manipulation?
Semantic information is one of the hardest things for a robot to get. Semantic scene parsing is still not there for manipulation in many cases. So I think that's exactly the kind of cognitively important information. So we are good now at, for example, executing motion plans with constraints, keeping an object level as you're moving it, or which objects should be held level and when. That's the kind of semantic information that's a lot harder. We have to solve AI to get that? I don't know. But I think that's exactly, semantic scene data is exactly the kind of cognitively important information that I'm referring to.
Let's see, the Santello results are very interesting, and but sometimes I don't know. I just want to try and beat it up one way or another. And so today, you brought up the Kemp object set.
Yeah.
Which I share your enthusiasm for. I think that we researchers have a real knack for finding a group of things that look like we've exhaustively sampled the world of all things, but inadvertently, of course, we've selected a set on which our system happens to work very well. And and I don't know how to get around that. And then Kemp and his group come along with this thing that's absolutely, outside of the prejudices of us robotics researchers, right? So now I look at that set, and just as you said, and I think. So here's the question: do you think that applies to Santello? And do you think that if you ran that same experiment with the Kemp object set, that you would get the same result?
I think there are a couple of things there to talk about. So to just answer the final question, I think my intuition is that yes. And why do I think that? After Marco Santello published that, people tried to poke holes and said, oh, what if you try other things? For other kinds of manipulation tasks, do you still find low-dimensional subspaces? And almost without exception, they did. So Nitish Thakur did work on haptic exploration. If you look at how the hand moves when the people are just feeling for objects, it feels like that's completely unconstrained, that you're not going to find low-dimensional subspaces, and they did. Other people looked at when you're crumpling paper or when you're turning the pages of the book. And again, they found synergies. They found very strong low-dimensional structures. They were not the same.
Right.
They were not the same. But most tasks happen to, for some reason, to have those synergies. So I'd be very surprised if you tried with the Charlie Kemp's objects if you found no synergies, if you found almost no low-dimensional structure. It might not be the same eigengrasps, it's not going to be the same subspace, but I still think you will find a low-dimensional subspace, even if you look at manipulation of Charlie's objects. That's my intuition. I don't have data to prove it, but that's what I think. Then the question of how do we select our object sets, that's a great one. And most of the papers, and I'm as guilty of that as anybody, we say, my algorithm worked on 87% of the objects that it worked in 87% of the cases on. And we're good about it. Usually in our papers, we also show the object so that the reviewer can make an informed decision. Is that a good set or not?
Yeah, don't interpret that question as a criticism of you. I think you and I and almost presumably everybody in that bag. My question was about whether Santello was a
And he did it too. He chose, I mean, they chose what to them felt like common household objects. So it's, Charlie's work, I think, should inform us more. And also, how do we get over this problem that everybody uses different object sets? I don't know, maybe the YCB object set is the way forward.
Now we're just substituting
We'll see.
sense prejudices for ours.
Well,
Much better prejudice to follow.
and Charlie's study was on objects prioritized by people with motor impairments. There are also other applications for robotics. If a robot is operating in a warehouse, right, it's doing order picking, presumably it's interacting with all the objects that people order for Christmas. So that'll be a huge set of objects. If a robot is in manufacturing, then it has a very specific set of objects it needs to deal with. So there will be different sets, yeah. Sid.
Thank you for the fantastic talk. One aspect of grasping that might be interesting is you talked about perception and about how you can deal with aliasing of object shapes to perceptual data. But there's also haptic data or tactile data or force torque data, receptor data that you're getting as you're performing the grasping action. How do you envision sort of incorporating that both into not just the planning algorithms, but also potentially the design of hands? You talked about how to shape your fingers, but there's also a question of where to put your sensors or what kind of sensors.
In terms of integrating that in your grasping primitives, I think that's a very good direction, because even if you take into account uncertainty from sensing, when we were doing that, we were still coming up with the best grasp, taking into account uncertainty, but then executing it open loop. At runtime, throwing in your tactile data, I think, is a good idea. How do you do that? The problem there is you have different things that speak different languages. The grasp planner will give you quality metrics for an object. Your perception algorithm will give you the fit quality of an object to your sensor data. The tactile information will give you a pressure distribution on your object. How do you bring all of those together so that ultimately you decide what to do? Maybe probability of success is the right language that everybody speaks, so you try to translate everything into how it affects your probability of success. Maybe a different framework is the way to go, but I think closing the loop while you're executing the primitive with tactile data is an excellent idea. How it informs hand design is an even better idea, and I think we're going to hopefully look at that in the next few years.
Oh, yeah. So I did an experiment with myself one time. So I'm interested in your experience with, with this fellow whose name I forgot, who has ALS.
Henry?
Henry, yeah. And I wonder, one time I did an experiment, I got one of those, toy gripper thingies, and I thought, okay, I'm going to use this all day, and see, it's better than any of the mechanical hands I've designed. Let me see how good is it, can I live with this device for a day or so. And I discovered a couple of things. One was, like, I could reach into the drawer and grab anything in the drawer. And then I realized that the drawer was actually full of things that you should be doing things with, like tools. A pair of scissors, roll of Scotch tape. Everything in there had a use. And so instantly I was faced with this next question, which is, oh, okay, sure, I can pick them up. Can I use them in the way they are intended? And the answer to that was inevitably no. There was no way I could start a roll of Scotch tape. There was no way I could operate the scissors and so forth. The other thing I discovered was that even I could pick things up. Maybe it's the same observation. Like, I wanted to use the watering can to water the plants, but I couldn't get it that high. It was too heavy, and I had a grasp that was stable enough just to pick it up and put it down, but not really to water the plant with it. So what I'm wondering is, I'm looking at what you guys are doing with Henry, and I think, like, the Halloween candy thing is cool, but how often does he say, oh, I would like to try this, and you guys say, no, that's not going to work. No, I would like to try that. You know what I mean? So do you have some sense of what sample of human activities could be done in this fashion?
My sense is, to give you a definitive answer, is that robots, I think enough tasks are doable in the foreseeable future to make a difference for somebody like Henry. Not getting a roll of Scotch tape, getting some Scotch tape off of that, and then, no, that's not going to be doable for a long time. Watering the plants, borderline. With some additional work, we could get it there. But you talk to Henry, and he gets it, right? He knows that he's not going to be able to do fine manipulation. But he tells us, first of all, I want to scratch my face. I want to pick up the razor and shave my face. I want to go to the fridge, get a bottle of water, and hold it so that I can drink. I want to get a towel and wipe my face. Those are things that he selected from the set of tasks that he felt are doable, and he was pretty spot on because he knew our robot and he knew us by that point. And he was telling us, this makes a difference. So we can do enough of those low-hanging fruit, hopefully, to truly make a difference. And then the other side of it was, can we really, out of what he wants to do 12 hours in the day, how much of that can we help him with? And Henry was saying, if you give this to me 2 hours a day, it'll make a difference. If you give a prisoner 2 hours of freedom per day, that person will live for those 2 hours. It makes a difference. So yeah, when we think of all the things that we do with our hands, it's scary and makes us want to switch fields, I guess. I don't know. But then we realize...
No, it means that it's a problem that will last your entire career.
Exactly. But there is enough low-hanging fruit that maybe we can do it. The watering the plants strikes me like exactly the kind of problem that we have a shot at, because it's a matter of, is that grasp stable enough that for something heavy we can resist this torque? It's a kinematic problem of the arm getting to the right places. These are problems that I think we have a handle on.
Have you tried to redesign the scissors to make them easier to use?
No, that's another possibility, yeah.
I mean, we now see these scissors that have really fat handles. Those fat handles have become more popular. And I read that they were developed for the handicapped who had a hard time grasping things. Fatter handles are easier to grasp. You can redesign it out there.
Yes, that's another thing that can help. So the Robots for Humanity project, we were collaborating with Charlie Kemp's group and Bill Smart's group, and Charlie Kemp was working on Henry shaving his face. And they instrumented the razor to the electric shaver to make it easier for the PR2 to slot in. To me, that's fair game. I mean, we can do it. It's probably not fair game to say that we'll have a robot that has a permanently mounted everything that it needs. It has an electric shaver mounted permanently on one hand, and in another hand with a pair of scissors, and in another hand with this. But to have these objects instrumented and the robot picking them up as they need to, yeah, that sounds reasonable. There are cases where that doesn't fly. Like I think for NASA, a big deal for them is for the robonaut to use the tools exactly as they have them in space, and they've been designed for the human hand. So for them, they don't like the idea of changing the tool to make it easier for the robot. So in some application domain, it doesn't work. For Henry, I think it's perfectly fine.
It kind of represents it's the upper part of the curve. It's bringing the task down towards where you can get it.
Right.
As opposed to making it less
So in all the examples you've shown, you've used like the camera which is placed towards the face. Have you tried placing the camera on the hand so that when you get closer you can get a better resolution on the perception?
We did. So my colleague Kaijen and Adam Leeper worked on this problem where they put a stereo camera in the gripper, and they did it works pretty well. To me, that's almost like having tactile sensing. It's a form of tactile sensing if you have an eye-hand camera. And some people make the argument that, oh, humans don't have eyes in their hands, so we shouldn't do that with robots either. But no, humans have fantastic tactile sensing, which never gets occluded. Cameras up here always get occluded when you manipulate. So yeah, putting a camera in the hand to me also sounds like fair game, and it's something that should be looked at.
All right.
Okay.
Let's thank the speaker again.
Thank you.